Our first lead-off speaker is Pramod Khaargonkar, the Vice Chancellor of Research and a Distinguished Professor of Electrical Engineering and Computer Science at the University of California at Irvine. With that, Professor.
Well, good day, everybody. It's really an honor to be part of this wonderful symposium and to be giving this lead-off address. Let me begin, before I start sharing my slides, let me just say I'm looking forward to the other speakers who will follow me for the whole session and then the discussion at the end. So let me begin sharing my screen. So the title of my talk is Fundamental Engineering Research to Societal Benefits. Let me begin with some personal comments so that you will know who is speaking. So I got my undergraduate degree in electrical engineering from IIT Bombay in India, and then came to the United States as a graduate student and got my master's in mathematics and PhD in electrical engineering at the University of Florida. One of my greatest good fortunes in life was that my PhD mentor was Professor Ari Kalman, who passed away a few years ago. The absolutely brilliant individual, founder of the field of modern control and systems theory. And his innovation that led to Kalman filter, it's basically a fundamental mathematical construct, has had enormous impact going back all the way to the space program and everything that has followed. Kalman filter is in many technological and beyond technological innovations. And then after my PhD, I rose through the faculty ranks at Florida, Minnesota, and Michigan. My own research, about which I won't say a whole lot, was basically or has been in fundamental control systems theory, and wrote many papers and so on and so forth in that field. I also have done some work which is on application of control systems theory, first to manufacturing, semiconductor manufacturing, and then reconfigurable manufacturing. Part of that work was supported by the National Science Foundation, ERC, at the University of Michigan, called Reconfigurable Manufacturing Systems. I also, very early in my career, received the NSF Presidential Young Investigator Award. So NSF has been at the foundation of my research career from the very beginning. In recent years, I have got interested in integration of renewables like wind and solar into the grid and the whole area of smart power grids. And even more recently, I'm beginning to explore some ideas on machine learning and control. My research has been funded by the National Science Foundation through multiple grants, by Air Force, by Army, by DARPA, and private industry. And in that process, I've also collaborated with many companies, including Honeywell, General Electric, Semiconductor Research Corporation, Xerox, and others. Besides my own research and its evolution, I have also had the good fortune of having had some leadership roles. So I was chair of EECS at the University of Michigan. Then I was dean of engineering at the University of Florida. My recent role at UC Irvine is as vice chancellor for research, where I'm responsible for the entire research operation of the university. But there are two other roles that I think are particularly interesting. I was the head of the engineering directorate at the National Science Foundation from 2013 to 2016. And a lot of what I say is informed by that experience. And for a short period, I was also deputy director for technology at ARPA-E. Enough about me. Here is the question I want to shed some light on from my experience. How does fundamental engineering research lead to societal benefits? And I'm going to do that through three examples. But before I sort of plunge into the three examples, Bill Bonvillian in his talk mentioned the Pasteur's quadrant. First observation is that much of fundamental engineering research is use-inspired basic research. Now, this quadrant representation makes it very hard boundary between pure basic research and use-inspired basic research. Reality is it's really a spectrum. You go all the way to pure basic science research with no interest in application, all the way to more applied engineering research. And so the basic research in engineering or fundamental engineering is in this sort of use-inspired quadrant. It's different from tinkering, and it's different from pure applied research. So the first example I want to discuss is semiconductor chips. It's an absolutely fantastic story of fundamental engineering research to societal impacts. And the story actually goes back a long time, even before the formation of National Science Foundation at Bell Labs, where the transistor was invented, and the Nobel Prize in Physics was awarded to Shockley, Bardeen, and Brattain for their discovery. And the citation is for their researches on semiconductors and their discovery of the transistor effect. So that was the birth of the transistor. And I don't think it would have become what it has become were it not for some other things that happened. So the next sort of big thing that I want to point at is the idea of integrated circuit. That is, how do you take a bunch of transistors together on a planar surface and turn it into a circuit which has some function? And for that, Jack Kilby from TI got the Nobel Prize in 2000 for his part in the invention of the integrated circuit. So another major advance recognized with the Nobel Prize. And then what we have done in the intervening years, and I'll come back to the starting point that on this chart you see around 1970 with some Intel processors. I'll come back to this in a later slide. Suffice it to say that we've been on this amazing curve of packing more and more transistors onto a small sliver of a chip, allowing for greater and greater functionality and making a whole technological revolution possible. So in this chart, what you see is a different sorts of microprocessors that have been developed since the initial Intel microprocessor to the latest, and the journey still continues. And now we are at 50, at least on this chart, it shows 50 billion transistors, whereas we might have started with, say, around 1,000 transistors. So it's been an astonishing scale up of transistor density. How did this happen? So one depiction of this, and this comes from Intel. So on the left-hand side is a series of innovations in the transistor itself, the core building block, and it is portrayed along with device geometry, which is articulated in terms of the line width. And this chart goes back to 90 nanometers line width. There is probably history well before we got to 90 nanometers. And then a series of innovations on transistor, on materials, on architecture. And so the way I like to think about this journey that we have been on is a coherent engineering research advances, fundamental advances in materials, in devices. This chart mainly focuses on devices, circuits, architecture. That's on the design side. And then equally important innovations on manufacturing. How do you actually manufacture these devices and these circuits and chips at the level of precision? It's an astonishing achievement of engineering driven by fundamental research. I can safely say that there are PhD theses and papers and NSF grants behind everything that you see on this chart. I just want to point to a program that I was involved in creating when I was at the National Science Foundation. It was a collaboration with Semiconductor Research Corporation, SRC. And here what we focused on was energy efficient computing, because energy efficiency is a key barrier. And we created this program to fund research in collaboration with SRC, going all the way from materials, devices to architectures. And that's funding many projects that will keep this evolution going. In 2006, there was a retrospective on Moore's Law, which is wonderful reading. And I just want to kind of point you to it. It's called Understanding Moore's Law, 4 Decades of Innovation. And what it does, it takes a look back. And it's a book that's available. I've linked it in my slides. So when we post the slides, you can go and download. There is one particular quote that I really love. And it goes to Gordon Moore, after whom this Moore's Law is named. And he stated indeed the technology-led science in a sort of inverse linear model. And Bill in his comments mentioned this, kind of very, very traditional notion that science is discovery and then you get technology. You get engineering and then technology. And I think that picture is actually not complete at all. And in fact, I will say some more about this towards the end. But here, Gordon Moore is actually pointing to a reverse kind of thing, where technology leads advancement in science. And in a way, Moore's law was a vision that led to major fundamental advances because we wanted to follow that vision. That was my first example to see how fundamental engineering research becomes a major sort of technological innovation. My second example is origins of Google. Okay, so in 1994, just as the internet and the web were sort of coming into reality, the web HTTP protocol had been discovered or had been invented. NSF launched an initiative in 1994 called the Digital Libraries Initiative. And the idea was, how can we use these digital technologies to turn all the human knowledge that's in our libraries and make it digitally available? It was a very forward-looking program, funded, I think, 6 projects under that Digital Libraries Initiative. One of them, and I've kind of taken a snapshot from the NSF awards, search Stanford Integrated Digital Library Project. The PIs were very, very well-known scholars, Molina Garcia and Terry Winograd. And on the top right, you see a nice picture of Sergey Brin and Larry Page. These are now household names. When they were working in this project. So both of them were part of this Digital Libraries project. And in fact, Sergey Brin was an NSF Graduate Research Fellow. He got one of the Graduate Research Fellowships. So NSF had a big role in Sergey Brin and Larry Page's evolution from graduate students to what was to come. In 1999, as part of this Digital Libraries project, they wrote a paper called the Pagerank Citation Ranking, bringing order to the web. And it has, Page and Brin and Rajiv Motwani, who passed away, too young, unfortunately, and Terry Winograd. And I just kind of, took a little abstract from that paper. So this is like the kind of papers that fundamental research leads to, is papers. And so they say, the importance of a web page is inherently subjective matter, which depends on the reader interest, etc. And this is their great insight. But there is still much that can be said objectively about the relative importance of web pages. So they're going from subjective to objective. And how you do that is through this mathematical algorithm called PageRank. So PageRank is a method for rating web pages objectively and mechanically, effectively measuring the human interest attention devoted to them. So if a kind of an indirect measure of interest in a web page and therefore its importance. So then they say we compare PageRank to an idealized random web surfers. We show how to efficiently calculate this thing and how to apply this for search. So you see the beginning of this idea of PageRank for the search application. Well, I don't have to tell you, Google is now one of the largest companies in the world. Certainly has a tremendous role in what we might call the IT revolution. And on this slide, actually, I've taken this from the National Academies. They've done a wonderful job of capturing the tremendous interplay between fundamental research in universities, R&D in industry, and then development of products and markets that eventually show up as products and services that all of our society enjoys. And so on the bottom side are the various fundamental research areas, and I've kind of captured them: digital communications, computer architecture, software, networking, distributed systems, database systems, computer graphics, AI, and robotics. Each of these, NSF has multiple programs in them. We funded research in foundational science behind and engineering behind all of these domains. And together, in an interplay manner, they have led to major companies, major innovations in broadband and smartphones, in microprocessors, personal computing, internet, cloud computing, enterprise systems, entertainment design. And the lines get thicker as the market size gets larger. So, so this chart takes for the largest size is $10 billion market, but now, we're talking about hundreds of billions of dollars of market. So it's one very nice picture that captures the entire technological revolution that was started by the semiconductors. Here, what I'm trying to do is to showcase the cumulative impact of what has happened. And in fact, on the left-hand side is a nice chart due to a very well-known economist, Carlota Perez. She studies technological revolutions, and she has gone all the way back to Industrial Revolution, and she points to 5 technological revolutions. And I've talked mostly about the 5th one, Age of Information and Telecommunications. And in fact, if you look at her description of the Big Bang for the 5th revolution, it's the Intel microprocessor announced in Santa Clara in 1971, which is why I started my story on the chips to 1971. So it's not the transistor, it's not the IC of Jack Kilby, it's the microprocessor. That's where the science becomes a technological revolution. Not taking anything away from our great scientists who made all this possible. And then she describes the previous revolutions as well. Look at the GDP per capita, $55,000, $60,000 per person, per capita in the Western economies. And it's the result of these technological revolutions. My third example is to sort of point to one topic that I think will be part of whatever might end up being the 6th technological revolution. That is still not clear as to what that's going to be. Machine learning, AI are going to be big parts of it. There will be bio and nano will be parts of it. And one part of it will be 3D printing, because again, the story is really, really fascinating. So the part of the story that I want to highlight here goes back to UT Austin and a very young graduate student, Carl Descartes, and his advisor, Joe Beeman. In 1989, they came up with this idea of a kind of additive manufacturing called selective laser sintering. And in fact, they got an NSF grant, which I have pointed, well, I don't have the NSF grant here, but they got an NSF grant, and I think Descartes also got some kind of graduate student support from NSF. The top right is a story in Austin American, talking about this revolutionary advance. Machine makes 3D objects from drawings. So you go all the way from a CAD drawing to a 3D printed part. And one of the very early patents that was given to Descartes for selective laser sintering is also shown. So it goes from this NSF-funded basic research to the very, very early patents. There was actually a very, very nice study done by IDA, and I linked the report at the bottom, that kind of went back over the entire development of 3D printing. And I've just taken a quote: NSF-funded precursors of additive manufacturing technologies in the 70s, development of computer numerical control machining and solid modeling, and turned early additive manufacturing patents in the 80s into proof of concept and prototype machines in 2 major commercial technology areas: binder jetting and laser sintering. So laser sintering is the part that was Descartes and Beeman. And this is the NSF grant that I alluded to in 87 to Joe Beeman. NSF role can be seen in fundamental research. So this paper is actually on the geometric modeling part that even preceded the selective laser sintering. IEEE computer, 1977. This was applying geometry and computing to represent geometry, which would then lead to the whole CAD revolution at University of Rochester. And on the right-hand side is the PhD dissertation of Descartes, again showing the foundational research enabled by the National Science Foundation that would then go on to become this whole revolution in 3D printing. Okay, 3D printing is McKinsey estimated is going to have a $500 billion impact by 2025. It's a global industry now, and there are applications in aerospace and all other kinds of manufacturing. I thought I would pick an example from something that one doesn't normally think of as application of 3D printing. It turns out actually that biomedical industry has had tremendous uptake of 3D printing. And so on this chart, which is taken from a very recent paper, 2017 paper that is linked at the bottom of the chart, shows dental implants and tissue constructs to biomedical devices. On the bottom left, that's the panel D. These are various kinds of biomedical devices that have been 3D printed, various kinds of tissue constructs that have been 3D printed, to drugs and their Raman spectra on the bottom right. So 3D printed tablets so that you can layer the various pharmaceutical ingredients in an optimal manner. So this is an example where a fundamental research area sponsored by National Science Foundation goes from fundamental research to societal benefits. So what's the lesson in all this? Well, it's clear that history shows us that there is a path that connects fundamental research to innovation, to technological revolution. I think sort of the big goal, big challenge, and aspirational goal for the engineering community is how do we get better at this? Because we need it badly. We need badly to connect fundamental research in engineering to societally relevant innovations leading to technologies that can solve societal problems. Let me make a couple of comments and then conclude. I think this is a big topic, and hopefully in the discussion we can talk more about this. NSF is actually a leader in trying to optimize this system and improve this system. So I want to point to NSF I-Core program, to Kurt Carlson's Value Creation Forum, to the recent establishment of the TIP Directorate. I think all of these are pieces of a larger puzzle on optimizing this system. So much to say about this, Ed, but with that, I want to thank you and thank the National Academies for inviting to be part of this wonderful symposium. Thank you very much.
Well, thank you, Pramod, for just a wonderful, wonderful talk. I have a few questions, but first as a comment, there is a company just up the road from you in Long Beach that you may know of called Rocket Lab, and they 3D print rocket engines. So it turns out when you look at they sent up for NASA a satellite called Capstone, and that satellite is in lunar orbit, and a very interesting lunar orbit called a nearly rectangular halo orbit, which is what NASA wants to use for sending people back to the moon. But the rocket that launched that was all 3D, not the whole rocket, but the engines in that rocket were all 3D printed. So, it's amazing how the technology gets used. I want to go back to something you and I were talking a little bit about before this session began, and that is how we communicate all of these amazing things, the Moore's Law and the integrated circuit, 3D printing that I think, I agree with you, will revolutionize people's lives. Obviously, Google has changed how people find everything. We who are technologists and researchers, I think, inherently understand all of this and understand what it takes to go from the initial research into getting it into the hands of the rest of humanity. But how do we get people to understand that process, and how do we communicate that?
I think that's a fantastic question, Ed, and there is much to say about it. Let me sort of begin by saying that the positive benefits from engineering and technology are so enormous that people just take it for granted. And so whenever we as researchers are doing anything, we need to be talking about our motivations, which are always to help society. That's what engineering is all about. So we should be talking about the human aspect of what we do and not just the technological aspect, so that people can relate to the motivations of why we do what we do. In that, we need to understand the broader ecosystem that we are part of. we get too readily focused on sort of a narrow slice of what we are comfortable talking about. But people really want to know the big picture as to how this whole thing comes together. And I think that's sort of what I tried to do in my talk today. There is another piece of this, Ed, that I want to mention. There is a science of science communication. That is, just because we are great at research doesn't mean we know how to communicate this so the public gets excited and is interested. So there is actually a science of this. Alan Alda is a big champion. I mean, he has taught us how to do this. And he's not the only one. I think there is a whole field of science communication. And I think if I had my way, every PhD student, maybe every master student would get a capsule course in communicating science to the public, because there is a lot to be learned systematically about how to do it well. We can get better at it.
Yeah, no, I as you know, we're talking, I absolutely agree with that. And both for people who are in academia and for people who are in business, I think we would all benefit from being able to communicate better the work we're doing. So the other question I have for you is, you started your talk talking about Professor Kalman and how important a mentor he was to you. As you've been a professor, how have you translated that into being a mentor for your students?
Oh, that's a great question. And I think, if I look back, it's been almost 40 years since I got my PhD, well, more than 40 years since I got my PhD. I think he was inspirational. So he inspired the best. He challenged us and inspired us. So that was one thing that I try to do, is to just challenge my students and raise their sights, right? I mean, what's possible? And I say that, you can do a lot more than, and a lot better than, a lot more impactful work. So I sort of, how do you challenge people to achieve their best and really raise their sights is a big part of what I do. And second is kind of the right balance between telling them what to do and giving them the freedom to explore. So I tend towards giving them a lot more freedom. I say that, look, I'm not going to micromanage you. You are an adult. I want you to go to your heart. What do you really want to do? And bring your creativity and bring your mind and heart together. And I'm here to make it possible. I'm going to help you. I'm going to do whatever is useful, but I'm not going to micromanage you, because I would rather see you grow up and become an independent researcher. And that was very much Kalman's approach to mentoring his students. He gave us a lot of freedom. Mm-hmm. He was always there to talk to, but he gave us a lot of freedom. So I try to emulate that.
And then since we have the time, my final question. You've talked about some things that were developed under NSF with NSF funding over the last 40 years or so, actually longer. What gets you excited now?
Big question, Ed. There are a lot of things. Probably the thing that really motivates me right now is the whole area of climate change and decarbonization of the energy system, because I see that as a major global problem with a huge opportunity in development of clean technologies, clean energy technologies, adaptation and resilience of our systems. One of the things that NSF did was create this Engineering Research Visioning Alliance, ERWA. And as it happens, just today they released the report on the role of engineering in climate change. And so I'm hoping that that sustained focus and emphasis on climate change and clean energy and decarbonization is such a huge opportunity and such a huge need, societal need. So that is sort of high in my mind, but there are many, I'm leaving out so much amazing stuff. We just had the mRNA breakthrough, right? So how do we build on the sort of vaccine thing into biomedical innovation? Another huge area that NSF can have a big role in, and many, many others.
Yeah, and as you and I were talking earlier, the ability to communicate to the public at large and the world at large how science and engineering impact climate change is obviously hugely important, and getting people to understand what we know and what we don't know, and Anyway, that'll have to leave that for another time. Again, thank you very much for your wonderful talk, and you'll be joining us hopefully at the end of the session as part of the discussion session.
I look forward to it.